We will now discuss the plot of the function, the fifth function in the list, the arctangent of the logarithm of the absolute value of x squared minus 1, right? Okay, the arctangent, the argument of the arctangent is can be any real number, so the arctangent has no problem, but there is a logarithm here. The logarithm, the argument of the logarithm is always non-negative, which is good, right? However, it can be 0, and it's actually 0 in 2 points, in x equal to plus or minus 1. So the domain of this function is r minus these 2 points, right? However, if we want to know what happens at those 2 points, whether the function is singular or not, and there's an asymptote, etc., we can calculate the limit, right? Let's say when x goes to 1, for instance, okay? Well, actually, to 1 or minus 1, doesn't matter, because the result is the same. In this limit, the function, the arctangent of the logarithm of this, well, the argument of the logarithm goes to 0. And when that happens, the logarithm goes to minus infinity. But there's an arctangent here. And the arctangent, remember, is a function that is, when the argument goes to plus infinity, approaches the value pi half, and when it goes to minus infinity, approaches the value minus pi half. This is the arctangent of x, all right? So that means that if this goes to minus infinity, then the arctangent goes to minus pi half. So it turns out that even though the function is not well defined at the points 1 and minus 1, the limit is well defined. So we could actually extend this function, even including these points of the domain, and extend it as a continuous function, right? Everywhere. Okay, so this is something that we should take into account. So there are no asymptotes at those points, right? The function has a well-defined limit. Okay, the next thing to do is, of course, to analyze. Well, there is a simple observation that can simplify the representation of this function, is the fact that this function is even, because it depends on x squared, right? So when you change x by minus x, the function remains the same. So it's an even function. So actually, we could only study it in the positive side and then replicate what happens in the negative side by making a mirror image. Okay, let's take now the derivative and see what is the behavior, the growth behavior of this function. So we first have to take this composition of 3 functions, right? So we have to take the derivative of the arctangent first. The derivative of the arctangent is this, the square of the argument, so the logarithm of this square. And then we have to multiply by the derivative of the logarithm. The logarithm of the absolute value of x is 1 over x, right? So this is equal to the derivative of the argument, 2x, divided by x squared minus 1, without absolute value, like this. All right? Okay, what happens, well, this derivative is well defined except for x equal to plus or minus 1, right? When x is equal to plus or minus 1, the denominator here vanishes, okay? And it does so, well, it actually changes sign on the one side of one on the other. Well, we'll see that later. But the point is, this is 0, so this is infinite, right? On the other hand, what we have here is something that goes to infinity, right? So this is 1 over infinity, so this is 0. So this goes to infinity, this goes to 0. So the limit is not well defined, right? We have an indeterminacy 0 times infinity here. So we have to resolve this, right? Well, we can make that in many ways, but perhaps the simplest is this. You have here, well, you take the limit when x goes to, let's say 1, right? Because by symmetry we can just analyze one of them, of this derivative, okay? So this limit is, well, the limit of the numerator is irrelevant because it's just 2, right? So we don't have to worry about that. So we only have the limit when x goes to 1 of, let's say, 1 over b squared x squared minus 1 plus x squared minus 1 times the logarithm of the absolute value of x squared minus 1 squared. Okay, right. Let's see. Here we have something of this form. Is u times log u squared. So what is the derivative? Well, what is the limit of this when u goes to 0, which is what happens when x goes to 1, the argument goes to 0, when u goes to 0. Well, there are many ways to analyze this. The limit of this is going to be 0. But there are many ways of analyzing this. Maybe the simplest one would be to, or maybe we can change the variable here, right? So we can say the logarithm of the absolute value of u is going to be t, right? So the absolute value of u is going to be e to the power t, right? So what we have here is the limit of, well, let's say the sine of u times the absolute value of u. This is u. So that is the sine of u. Well, it means on the right and on the left the limit is different. So let me just distinguish, right? Let me call this. Let me calculate this first on the right. Then if we are on the right, then u is positive, so it's equal to the absolute value. So what we have is the limit when t goes to minus infinity, right? Because when u goes to 0, t goes to minus infinity, of et times t squared, right? Actually, it would be better if we put it here minus, right? Minus, and then here we make the limit when t goes to plus infinity, right? So we have this, okay? We have t squared e minus t. And you know, just using perhaps L'Hopital twice, that the limit of this is going to be 0. And you can do the same thing with when the limit of this goes to 0 minus of u log the absolute value of u squared, right? And it's the same story, okay? You have to take the logarithm of the absolute value of u, make it equal to minus t, so the absolute value of u is is e minus t, okay? And then the limit here is the limit when t goes to infinity, all right? And u is negative this, so minus e to minus t, and then you multiply by minus t squared, which is t squared here. Again, doesn't matter whether you have a minus here, the limit of this is going to be 0, so the limit when u goes to 0 of this expression is 0. So now, if you look at this is what you have here, right? So this expression, this whole expression in this limit is going to go to 0, because it's exactly the limit we have analyzed here. So we have 0 here, 0 here. So this limit is plus infinity. All right, plus infinity. What that means, but not plus infinity, sorry. Yeah, no, it's plus infinity. Yeah, that is okay. It's plus infinity. So what you have here is a vertical slope, vertical tangent. Okay, vertical tangent. So we know that at the point 1 and minus 1, of course, because of the symmetry, the function has a well-defined limit, but the tangent there is going to be vertical, right? A vertical line. Okay, so it's got a cusp, and a very stingy cusp, by the way. Okay, so now we need to analyze what is the sign of this derivative, right? Which is something that we haven't analyzed so far. We don't have to worry about this factor here, because whenever the derivative can be evaluated, this factor is going to be positive, right? So we only have to worry about this. And the sign of this depends on x, whether it is on the left of 0 or on the right of 0 and of 1 and minus 1, right? So let's say if x is larger than 1, then this is positive, and this is of course positive, so the derivative is positive, right? If x is between 0 and 1, then this is negative, this is positive, so this is negative. If x is between minus 1 and 0, then this is negative, so it's going to be positive, which is also something that we could have guessed because of the symmetry of the function. And finally, if x is smaller than -1, then this is positive again, and this is negative, so the product is negative. Again, this by symmetry, if here the function grows, here must decrease because of there's a it is a mirror image in the negative side with respect to the positive side. Okay, so we have a function that decreases, then increases, then decreases again, then increases again, right? All right. We could analyze the concavity, but I don't think it's necessary because it is something that can be inferred from these constraints on the function. So if you put this information together, you're going to get this picture. This picture here, right? Okay, well, there's some piece of information that I haven't analyzed, which is what happens when x goes to plus or minus infinity with this function. And that's easy to analyze because when x goes to plus or minus infinity, okay, when x goes to plus or minus infinity, the argument diverges, the logarithm diverges too, so it goes to plus infinity in both cases. And then the arctangent of plus infinity is pi half. So there's an horizontal asymptote at pi half. That is the last piece of evidence that we needed to use. So there you go. This is the horizontal asymptote, right? The function, as I said, is equal to, let me just make it a little bit more stringent here. So it's equal to minus pi half at the points 1 and minus 1. Well, it's not equal to that because the function is not defined there, but the limit is well defined, and the limit is exactly this value, right? So the function approaches this value with a vertical tangent, as we have analyzed here, with a vertical tangent, right? And then, as we have seen, just focusing on this, on the positive side, this function decreases first, then increases, right? So it must have this behavior, okay? And it also, at the point 0, the value of the function is 0. That's easy to see because we just have to put here 0, then you have the logarithm of 1, which is 0, the arctangent of 0 is 0, so f of 0 is equal to 0. So we know that this function touches this point, okay? So the function behaves like this, like a parabola. It's not a parabola, but it's a parabolic-like behavior here. The slope here, by the way, is infinity, right? Okay. And then it grows. And since it has to approach this, the growth is like this. So if it goes from slope 0 here to slope infinity here, then it has to behave like this, so it is concave. Same as here, if it starts with infinite slope and then it decreases slope until 0 slope at infinity, then it is also concave. So we don't have to analyze the concavity to guess that this function is going to be concave everywhere, right? So that is what the function looks like.